This is Benzene Clayton reviewing the official ACS guide to organic chemistry. So I'm going to go back to first semester. ACS exam is mostly the second semester stuff, but it's about 1/3 of the last semester items here. And I'm going to page 41 here of the ACS book here. And let me do problem number 24 of page 41. What we see here is a problem that discusses here first thing here in the problem is we encounter the question here, which one would form a racemic mixture? You have to know the definition. Racemic mixture means an equal 50-50 mixture of R and S isomer if it is just one stereoisomer, one stereocenter rather. And then here you see that we are reacting one of these double bonds with the hydrogen. Here they use platinum instead of palladium, but don't worry about that. This is a hydrogenation, meaning the double bond is going to disappear. We look through all of these here, that one, that one, that one, and that one. All those double bonds will disappear if we do a hydrogenation. So what this is asking then with this is which one would form a stereocenter, because when you do a hydrogenation on an alkene, what's going to happen is that flat double bond, whichever one it is going to react on both sides. Anytime you have a flat starting material or flat intermediate, you usually will always get a racemic mixture if it forms a stereoisomer, or if it has a stereocenter that is formed in the reaction. So let's analyze this thing here. If we let's draw it right here on the side of my paper. Excuse me. Here, this is how they represent benzene rings here. I'm just going to abbreviate that as pH. So here's where the alkene was. We see if we do a hydrogenation reaction here with the H2 and platinum, which is the catalyst, it's going to form this. This is what we remember from practicing our reactions. But if you remember the specifics here, hydrogen will add on both sides right there. This right here is a stereocenter. And since this is a flat starting material, when it reacts, it will form on both sides here. So you'll also get the hydrogens that are coming out of the plane here. Okay, so that is actually the answer, A. If you notice these, both of these, when they add here and here, they will put two H's here on each of these carbons, so neither one of these are even possible because they have two of the same. Here for a stereogenic center, you have to have 4 different things attached. Things can be atoms, or they could be lone pairs, but usually it is atoms, so it has to be 4 different atoms on a carbon. And the other thing is it has to be chiral, and having a stereocenter is one thing that causes chirality. Well, continuing on here, if we hydrogenate this stereocenter disappears. You see that one right there on the ring. That stereogenic center disappears. So now, very briefly, A is the answer on that, but I want to go into a little bit more detail. Let's look at this problem right here. Let's determine the stereochemistry. I'm going to draw all the benzene rings out so we can see this. This is one of the isomers here. Okay, there's one of the stereoisomers. That's with the hydrogen going back like this. If it was not pointed back, to determine the stereochemistry, we would want to flip everything around. So we want to turn that 180 degrees. If the hydrogen now is pointed forward, we can determine the stereochemistry, but we have to remember to flip whatever we get. Okay, with the rules here, in determining the R and S system here, we go out one bond at a time here. I showed everyone in class here that you would just count like that. At the end of each bond here, we have carbon, carbon, carbon here on 3 sides, and then hydrogen. This automatically gets the lowest priority, which in the R and S system is number 4. The next thing here will be to go out additional bond lengths until we reach the first point of difference. So here, here, and then here. We actually have to draw in the hydrogens here to go out an additional bond length here. These 3 hydrogens are on at the bond length of 2. We go out 1 bond length here. We have a carbon that's going down here. We have 1, 2. Okay, and then going down this little branch here with the benzene ring, we have 1, 2 on this side of the ring, and then 1, 2, 2, because we have to count this double bond twice. Multiple bonds get counted multiple times on both sides of the double bond. Okay, so let's make the list at the 2 bond distance. On this side we have 1, 2, 3 carbons. So at the end of each of those we have 3 carbons. For this one here, let's make a list. Each of these we got at the bond length 2, 1, 2, 1, 2, 1, 2. We have 3 hydrogens. And then here we went down 1, 2. We have 1 carbon in this list. And there's probably going to be 2 hydrogens. They're not actually shown. Here they are. I'll show them like that. 1, 2, 2. So that is the rest of that list right there. Oops, ran out of room. Now we can see that this is the lowest priority in the first one of the list, because H is lower than both of these C's here in the first position of the list. And so that is going to get priority number 3 right there. And then here we have a comparison of these two. Here you always arrange a list listing the highest atomic number first. That's what I did here. Those are the same, so we have to go to the second atom in the list. Don't go to the second until you've looked at the first. But we're only looking at 1 atom at a time here is the key. Here you see that this is the first point of difference in these 2 lists, and that one is lower than that one over there, so that's priority number 2. We've determined that this is the highest priority, is that benzene ring. Now the next thing here is to do the organic chemist version of the peace sign here, or a Y, however you want to look at this. And the hydrogen's pointed back, so I don't have to rotate anything. I'm considering this is number 3, which is that methyl group right there. Okay, this CH2 in the benzene ring over here is number 2. That whole benzene is number 1. And then we follow the arrangement of numbers here in numerical order. This isn't something actually moving around. All it is we're seeing the direction of order. And there's our peace sign there, the organic chemist version of that. And then you could see it's going, this arrow is really, it's pointed to the left. Left used to mean sinister. Sinister here is S, that is the S configuration. If it were going in the clockwise direction, that would be R, or in the right-handed direction. Okay, and that's a short review there of the stereochemistry. This is a S configuration around that stereo center.